The first speaker allows me to make a long introduction short. It's our host, Tarmo Pukkila, and the theme of his paper is on the ordered determination of time series models. Please, Tarmo.
Thank you, Peter. Ladies and gentlemen, the title of my talk is on the order determination of time series models, and it is a kind of starting point was the time that I spent at the University of Pittsburgh, the academic year 1985-86, with Professor Krishnaiah and Dr. Rao. Unfortunately, Professor Krishnaiah could not attend this conference, namely some of the results are in this presentation are based on our joint work. As we will see, the title of this paper might be a little bit misleading, namely it is more how to specify Arma models, what are also called after 1970 Box and Jenkins models. The paper is based on order determination criteria, and what I'm going to do here, I'm going to give a kind of recipe how to try to solve or in a different way this very difficult problem. First, let's look two references, two technical reports, papers which I wrote jointly with Professor Krishnaiah in Pittsburgh. The titles are almost the same. The only difference is here is univariate and here is multivariate. These present word processing systems are so nice that you can get two papers by changing one word. And they are on the use of or the regressive order determination criteria in white noise tests or white noise tests for time series. Of course, one important reference here is the very well-known book of Box and Jenkins, first published in 1970. Where we learned how to build Arma models. That is, we learned what was called identification, estimation, and diagnostic checkings. Let's look a little bit more closely at the problem. We consider Arma models which can be represented in this form. We have the autoregressive operator phi and moving average operator theta p. We assume that these polynomials have their zeros outside the unit circle. This makes this what are called stationary and invertible models. We assume that the observed time series can be made stationary by differencing the time series d times, and mu is the mean of the time series. Then we can, if we have a stationary situation, we can express the time series in a well-known fashion as an infinite moving average or as an infinite order regression. Now, before going to the details, I would like to take one model selection criterion, which in time series context, which can be expressed in this form. This is multivariate case. This is sigma means the covariance matrix of the innovation series AT in that model. n is the number of observations, and then k means the dimension of the process, how many time series we have at the problem. One result in that joint work with Professor Chris Naeve was that if we consider autoregressive situation, the behavior or the performance of this criterion depends on k, in such a way that if we have n fixed and increase k, the dimension of the process, then this kind of criterion has tendency to estimate the order to be lower and lower the greater k is done. And that's one thing. I have a few copies over here on those two papers which I mentioned in the beginning. As I told, the method is based on model selection criterion, and there is not so much new in the method, namely how I specify a model is exactly the same way as, for example, is well known in the book of Box and Jenkins. That means in diagnostic settings, we pay our attention in the residuals. One possibility, if we have a stationary case, one possibility is, of course, to use, if we have an Arma situation, here we have P and Q, the orders of autoregressive and moving average operators. We could set, let's say, maximum order, what we consider, let's say, P star and Q star, and then estimate all of the models in this grid and select that model that makes the order selection criterion, let's say delta PQ is n multiplied by log sigma squared hat plus the number of parameters p plus q, and then this, let's say, penalty term c of n, which might be, for example, log of n, and sigma squared hat is the maximum likelihood estimate for the innovation variance. There are several problems in this kind of approach, and one is at least the fact that suppose that we have, for example, Arma 1 situation, Arma 1 model has generated the data, then in this kind of approach we have to estimate unidentified models, I mean unidentified in the traditional econometric sense. And that's one problem. There are also estimation problems if we have unidentified models. And in practice it is very difficult to know what those maximum orders P star and Q star would be. And so how I approached this problem, the idea is that we estimate models starting from we test whether we have P is equal to 0, Q is equal to 0. That is, we test whether the model or the time series is white noise or not. If it is, we have solved our problem in the world of linear models. If the white noise hypothesis is rejected, then we move to the one-parameter models. That is, we consider these models and look at the residuals. If the test does not reject the white noise hypothesis, then we can select the model, and so on. We continue as long as we meet the situation where the test does not reject the null hypothesis. And in this approach, I have combined how to select the degree of differencing. If Cn, for example, is log of n, then we have a consistent criterion. How do I test whether the residual series is white noise or not? In those two papers, I and Chris Naeve, we used autoregressive models to test whether a time series is white noise or not. That is, we selected the order for the time series by using an autoregressive order selection criterion. And one of the best was this criterion where the penalty term is log of n. If that order selection criterion gives the order 0, then we have AR's 0 model. That is, the order is 0. That means we have white noise case. And in this way, in fact, we have rather effective way to select the order for the time series. I won't go to the details of the method. Let's look at some examples taken from this book, Box and Jenkins, 1970, where the authors consider, among other things, these time series from A to F. These are all of these are considered to be non-seasonal time series, and using this method, we end at the following result. Using this method, and BHA means what is the identification when we used the technique proposed in the book by Box and Jenkins. And these tentative models, they are arrived at by using autocorrelation functions, that is the autocorrelation and partial autocorrelation functions. And we see that if we consider, for example, this series A, we see that the tentative models are, here we have a non-stationary situation, and here we have Arma 1 stationary Arma 1 situation. The method which I have used here ended at a stationary AR1 model. In other cases, the two methods arrive, roughly speaking, at the same results. There are, however, some interesting things happening in this series. If we consider subsections of the series, that means we try to test whether the observed series are stationary or not, and we observe that for time series A, the observations from the first 100 observations lead to AR1 process, AR1 model, as well as the last 97 observations. In the case of series B, if we consider again this kind of subsections in the series, we end at the models where in 3 cases we have random walk situation, and in 1 case we have for first differences we have AR1 model. And if you look, for example, at the spectra, if you estimate the spectra, there are some signs that the first differences might not be stationary. And also for time series C, we see that there might be some stationarity problems as well, and the situation is the same for the time series D. There are at least 2 practical problems in this approach. which should be solved. One is how to estimate the model, and the second, how to calculate the residuals from an Arma model, which is stationary and invertible. Now let's take an example, a very simple example. A stationary and preferably invertible MA1 model like this. Xt is equal to at minus theta at minus 1. Hänen and Rissanen in 1982 in their biometrica paper, they considered the problem how to estimate, how to obtain initial estimates for the parameter theta, and what they did is to approximate a model by a finite order regression in this fashion, and select in a certain way the order L, and then we obtain the least squares residuals for, and which estimate at, that is, we obtain at hats. And then these can be plugged here in this fashion. Xt is equal to minus theta at minus 1 hat plus at. And in this way we can obtain the least squares estimate for theta. Now, because if we think about the least squares residuals, they are estimates of at. That is, in fact, the true innovation at is equal to at hat minus the error term, let's say epsilon t. If we look at this original model and replace these ATs here in this equation, we obtain the result xt is equal to at hat minus epsilon t minus theta epsilon a t minus 1 hat minus epsilon t minus hat. That is xt, we obtain the model xt is equal to xt minus at hat is equal to minus theta at minus hat minus at plus theta at minus 1. Now this is in fact the TLS kind of situation. We have a linear model where we have error term, which is again MA1 process. And what I have done here, I have obtained the estimate, the initial estimate for theta using the method proposed by Hänen and Rissanen, and then continued to the TLS stage and obtain a refined estimate for the parameter theta. This procedure can be iterated. And we can obtain again the TL estimate for the parameter theta. And that's how I have proceeded. The second thing is, as I mentioned, is how to obtain the residuals from an Arma model to test whether residuals are like white noise. For that purpose, I have used Cholesky decomposition, and that makes it possible to obtain the estimates also in the case where the parameter is outside the invertibility region. Finally, what this method really does, it provides us with a non-stationarity test. It is a kind of byproduct. I made a small simulation study on the basis of the paper Dickey, Bell and Miller from the year 1986, where they study whether in an AR1 model the parameter phi is on the unit circle. That means if it is exactly 1 or less than 1. And these numbers dpm are from that paper, and these numbers, here is the phi parameter theoretically, here are these numbers in the cases n is equal to 50, n is equal to 100. What is the power if we use this kind of model selection criterion as a test of stationarity? And as we can see, these numbers are rather close to each other. One property here in this kind of approach is that if we use a consistent order determination criterion, then we have that kind of situation where, if we think traditionally, we have the situation where alpha, the significance level, approaches 0 with increasing n. And it is a kind of a coincidence that when we use log n criterion, then the significance levels are rather close to those significance levels what applied people every day use. Thank you.